and you are of course most welcome. This is Project Euler problem number 7. So very simple, what is the 10,001st prime number? Now, there are three ways to solve this. The first is to read in a list of primes that you might have found from the internet. That's kind of easy, we're not going to bother with that one. The second one is brute force. So this one involves a primality test. So we're just going to cycle through every odd number, say 3, 5, 7, 9, etc., until we find the 10,001st prime. So we will need a primality test, so I'm going to install mine from SymPy. From SymPy import is prime. If you don't have SymPy, you're going to have to find the code on some website somewhere. From SymPy import is prime, and I'd like to time this as well. So from time import time, and then we'll start the clock here. There we go. Right. So we want to cycle through all the odd numbers except those that end in 5, because none of those are prime except for 5 itself. So if I set current number to 5, at that stage we will have 3 primes. So primes found equals 3, 2, 3 and 5. Right, so then we'll cycle through all the numbers that end in 1, 3, 7 and 9. So while primes found is less than 10,001, if current number, so the first thing we'll do is increment the next odd number. So if current number mod 3 is mod 10 is equal to 3, then we can add 4. So current number plus equals 4. So then it will go from 3 to 7 and avoid the 5. So it'll save a little bit of time. Else current number plus equals 2. Then we do the primality test. So if is prime current number, then primes found plus equals 1, and this while loop will just keep running until the number of primes found is 10,001, and then it will spit out the answer. So current number, and we want to know how much time that took, so time minus start. That should get us the correct answer. 0.466 seconds. I'll just run that again because that looked like it hung for a bit. 0.37 seconds. Let's do one more. 0.29. Why is it speeding up? 0.29, 0.28. So it looks like it runs at about 0.29 seconds. Okay. This is okay as far as it goes, but if we wanted to scale this up to find, say, the 10 billionth prime number, this is going to take ages. So we need a quicker method, and indeed there is one. So you may have heard of the sieve of Eratosthenes. Sieve the 2's and sieve the 3's, the sieve of Eratosthenes. I don't remember the rest of the poem. So let's say we want to find all the primes below 20. We'll include 0 and 1. So I want you to imagine that these numbers are the indices of a list of booleans. All of the booleans are initially set to true, so we assume that all these numbers are prime. And we're going to systematically sieve out all those numbers that aren't prime. So 0 and 1 are not prime, so we'll set them false right at the start. And we come to the first prime number, which is 2. Now all the multiples of 2 are going to be set to false because they're not prime. So 4, 6, 8, 10, 12, 14, 16, 18. There we go. So all the multiples of 2 have been marked false, so they are not prime. Now we go to 3. 6 has already been marked, 9 hasn't. 12 has been marked, 15 hasn't. And that's it for the 3's. Now we go to 4, and we can see that 4 is already marked as not prime, so we skip that. We go to 5, and now we have exceeded the square root of 20, so we can stop, and all the numbers that are still marked true are prime. 2, 3, 5, 7, 11, 13, 17 and 19. So, and we can see the 6th prime, 1, 2, 3, 4, 5, 6 is 13. So there we are. Now I'm actually going to get rid of this Chrome window because I want you to see the output. I don't like people seeing the answer usually, but I mean, if you copy the code, this code here, then you'll get the answer anyway, so it doesn't matter. So let's code this new solution using this sieve of Eratosthenes, and it goes a little something like this. So def sieve, and we'll set limits. So this will sieve all the primes below a certain number, and we're going to pretend we don't know the answer is 104,743, and we'll say we'll sieve all the primes below 150,000. So okay, what are we going to do? So first thing we do is set up the list of booleans. So list of primes equals a set of booleans all set to true and with size limit. There we go. So the first one, so the next thing to do is set indexes 0 and 1 to false. Okay, right, next thing, we're going to start sieving. So we'll start sieving at n equals 2, and we'll stop when n exceeds the square root of the limit. So while n times n is less than the limit, excuse me a second. Okay, so while the square root of n is less than the limit, we will do our sieving. So we don't want to sieve for n if list of primes n has already been set to false. So if list of primes n, and this just means if list of primes n is equal to true. So you could put equals true if you want, but this just means exactly the same thing. So if list of primes n is true, then we do the sieve for I in range. We want to start from 2 times n. We want to stop at the limit, and we want to increment by n. And then it's list of primes I equals false. We're setting all the multiples of n to false. Then when that's done, we want to set n plus equals 1, so we increment n. I think that's it. Return list of primes. So this function will return a list of booleans representing all the numbers within the limit and denoting them as true or false as to whether or not they're prime. So if I say print, if I set this up properly, limit will set to 150,000, and then primes will be the list of booleans which we'll get from this sieve. So sieve limit. And then let's say I want to do print primes, say 277. I don't know if that's prime, or primes 3081. And let's see what that does. True and false. So 277 is prime, but 3081 isn't prime. Obviously that divides by 3, so of course it's not prime. Anyway, so we now know for all the numbers below 150,000 whether or not they are prime. So what we do is we now loop through all those numbers until we find the 10,001st prime. So for I in range, start with 2 because we know that's the first prime number, and going up to the limit. Do we need some? Oh, we need number of primes, don't we? So number of primes equals 0. So if primes I, so if I is a prime number, then number of primes plus equals 1. Then if it's the 10,001st prime, we need to come out of the loop. So if number of primes is equal to 10,001, then print I. We want to print the time it's taken as well, so I'm going to set the clock here, mid equals time, and I want to print off I and mid, oh no, time minus mid. So having printed off the correct solution, we then want to break out of the loop, and I think that will do it. Looks okay to me. So we'll run both of these algorithms and we'll compare the difference in time. So here we go. Right, so the first algorithm took 0.28 seconds. The second algorithm took 0.06 seconds. That's quite an increase in speed, so I'm quite happy with that. So that is problem number 7, and this is Project Euler problem number 10. The sum of the primes below 10 is 17. Find the sum of all the primes below 2 million. So if you're one of the 0 people who watched the episode on problem 7, I think the solution here is going to be pretty much the same. So brute force is to just loop through all the odd numbers except for the ones that end in 5 until we have the 2 millionth prime. So something like this. Number of primes, we'll set that to 3, and current number, we'll set that to 5. And then while number of primes, oh, also we want the sum. So the sum of primes, 2 plus 3 plus 5 is 10, so we'll start there. While number of primes is, oh no, we want the current number, don't we? So while current number, because we want all the sum of all the primes below 2 million. So while current number is less than 2 times 10 to the 6, that's quicker. If current number mod 10 is 3, then we go forward 4. So we want all the numbers ending in 1, 3, 7 and 9. So current number plus equals 4. In all other cases, current number plus equals 2. And then we do is prime. So I'm going to bring in the is prime function from simpy import is prime. And then, so if is prime current number, so we want to increment the sum of primes plus equals current number, Number. Oh, do we need the number of primes? I don't think we actually need the number of primes, so I don't even know why we're storing that. So number of primes can go away. Sum of primes is fine, and then that's it. And then right at the end we print sum of primes. Right, that is going to take a little bit of time, so let's see how long it takes. Time minus start. Let's go for run. Yeah, this is taking a fair old time. Well, that found the correct answer, and it took about 8 seconds. So, as I stated in the problem 7 episode, the quicker way to do this is to use the sieve of Eratosthenes. I'm not going to show you how to do that again, just go back to episode 7 and it's all in there. So, let's get some space. Right, so the sieve of Eratosthenes. Let's see if I can do this from memory. So def sieve limit. So we need a list of booleans. So primes equals, they all got to be set to true to start with, and size will be limit, and then primes 0 equals primes 1 equals false. Okay, so n equals 2, and then while n times n is less than limit, if primes n, should we say if not primes n? Yeah, if not primes n, so if, oh no, it is if primes n, so n primes n has got to be true. If primes n, then for I in range 2 times n, limit n, in fact I might just tack this on to episode 7 because they are so similar. So right, where are we now? That's my favourite Bowie song, that. Where are we now? Right, we're going to set all the non-primes to false. So primes I is false, and then we increment n. Then we return the sieve, return primes. There we go. So we know that the limit has got to be 2 million. So sum of primes, so another variable called sum of primes. In fact, it's the same variable, I'm just going to set it back to 0. And then for I in range 0, we'll start with 2 to limit, if, oh, we got to get the primes, haven't we? So p equals primes limit, if p I, then sum of primes plus equals I, and then right at the end print sum of primes. Let's see which of these is quicker. I think the sieve method will be quicker. We'll just check. So let's set a clock here. Oh, it doesn't like that. It's got to be sieve there, not primes. So we'll do that, sieve. There we are. Right, sum of primes, and then we want the time it takes. So time minus mid. That should just about do it. So I'm going to run both of them again and we'll see how long they both take. Yeah, so the second algorithm took 1 second. First algorithm took 8 seconds, so it's about 8 times quicker. So yeah, that's it. And as this is going on to the end of problem 7, I will see you next time for the problem 8.